Okay, hi guys, good morning. So how many of you are there? You have 3 of you. Okay, we'll just wait for 2-3 more minutes. Let your friends join. By the time you can text or call your friends and ask them to join soon. In Chennai, how's the climate, guys? Because I'm not in Chennai.
Sir, it's the same, sir.
It's the same. Bangalore is like extremely cold. Now I went out for a chai. Oh God. That too, guy for a guy who's from Chennai. Very difficult. This cold climates. Actually, Bangalore will be like very, very hot in summer and very cold in winters. Like Bangalore, Delhi, all these places have the same weather patterns, extreme climates. Chennai is tropical climate. Like it's hot or it's less hot. Right? You can never see cold winters in Chennai. No, waking up is also difficult in this climate. Actually, in Chennai, you wake up little early. Like it's why it is. When I was in Chennai, it was little easy for me to wake up. But yeah, here it is little difficult. Actually, I was before starting this XII classes when I was teaching in Byju's. There used to be no this morning classes and stuffs. Right, we have only evening classes only on Saturday and Friday, Saturday, Sundays. So I was never a morning person. Right, but yeah, now the situation demands. Right. So if you guys are able to wake up and come, why not me? Right. Okay, guys, we have 4 of you. Maybe we'll just wait for 1 more minute. Okay, guys, I think we'll start. Okay, let your friends join when they want to join. Let me share my screen. Okay. Right. Fine, guys. So we have been saying thermodynamics, right? Okay. So we saw, I think, thermochemistry. Thermochemistry we have been saying, and I think we did a good amount of problems. I think now you would have understood where to apply what, how to write the equations. Say for a single reaction, you'll be able to connect bond enthalpies, bond dissociation enthalpies, and enthalpies of formation. Okay, I would say these 3 are the most important things. Okay, fine. Now, other than this, I have a few other enthalpies also, like depending on different kinds of reactions, right? Say in that context, right? So we have, right? So we have enthalpy of neutralization, right? So it's called delta H and U, right? So I think from the name itself, you can understand what I'm trying to say, right? So here I'm going to have, what to say? Acid-base reaction happening. You know what is neutralization? Acid and base reacts together to form salt and water, right? Okay, so now please understand, guys, if I have a very strong acid, right, and if I have a very strong base, the reaction goes to almost 100% completion. Is it not? And as the acidity increases and as the basicity of, or the basic strength of the base decreases, the percentage completion of the reaction also decreases. Is it not? Right? Obviously, a stronger base and a stronger acid will react faster in the sense that they will almost go to completion. Right. So whenever you have a strong acid, I'll write SA. Whenever you have a strong acid, you don't have to include the anion. Basically, you know, you'll have H plus ion as well as the counter ion, anion, right? So whenever you have a strong acid, you don't have to represent it with, I mean, you don't have to represent the counter ion. It is suffice to just write H plus. Okay, in the reaction I'm telling, when you're going to write the reaction. Okay, so same way when I have a strong base, again, in that case, you don't have to talk about the counter cation in the sense that, say, if I have NaOH, it's a strong base, right? So you don't have to specify that Na plus is present. You can just directly write it as OH minus, right? So now whenever you want to write a reaction, the neutralization reaction, and if it's a strong acid and a strong base, you just write this reaction. So when I have a strong acid plus a strong base reacting, I write it as H plus plus OH minus, giving H2O, as simple as that. Okay, right. Now please understand, guys, since we are taking, see, we are going to have some, I would say, assumptions here. Okay, so there are, say, some handful of good strong acids. Okay, now like the thing is, all strong acids, and if they react with strong bases, the enthalpy of neutralization value, that is obviously for this reaction I'm talking about, the enthalpy will be a constant value. Say, for example, if HCl is a strong acid, if it reacts with NaOH, that will have one value. Say, if I'm going to have HNO3, again, it's a stronger acid, again reacting with a strong base, will have the same value of enthalpy of neutralization as the HCl reaction. So what I'm trying to tell you is that I just have strong acids, right, and weak acids. Weak acids will, say, different weak acids will have different values. But what I'm trying to tell you is that all strong acids will have same value of enthalpy of neutralization. Okay, will have same value of enthalpy neutralization. Say in this H plus, it doesn't matter where it comes from. As long as it is coming from a strong acid, the enthalpy of neutralization value is going to be a constant value. Okay, and that value is 53.7 kilojoules per mole. Okay, you have to remember this value, people. I like, again, I would like questions coming from this very rare, but still, if it comes, like, you have to remember this, right? So this is a constant value, 53.7 kilojoules per mole. Okay, right? And I think it is in terms of calories. I'm not sure. I think it is 13 kilocalories, but please check it, right? Maybe I'll even tell you before the class ends, maybe, right? Okay, so if, as long as this and this coming from strong sources, strong acid and strong base, this is a constant value. Okay, now actually it is better to give a definition. We gave definitions for all the other enthalpies. We'll try to give a definition for this also. Please check down the definition, people. Enthalpy of neutralization. Okay, so it is the enthalpy change occurring. It is the enthalpy change occurring when 1 mole of the acid, is neutralized by a required amount of base. When 1 mole, when 1 mole of the acid is neutralized by a required amount of strong base. You please write as strong base, not just a base. Okay, right? So guys, we are actually not going to concentrate on the base here. We are always going to concentrate only on the acid. Okay, so if it's a strong acid, you know how to write it. This is how you write the equation, right? And if it's going to be a weak acid, now how will you write the equation is the question, right? Say, for example, if I tell you that enthalpy of neutralization of HCn's hydrocyanic acid is some X, Okay, now how will you write the reaction for this? Now HCN is a weak acid, guys, so you cannot write it as H plus. You have to write the full acid in the sense that you have to write it like this, HCN. Now the base is always a strong base, okay, because that is what is given in the definition, right? So HCN reacting with OH minus will form H2O plus, I mean basically H plus, and OH minus combines to form H2, and what is remaining is Cn minus. And for this reaction, enthalpy is X, right? For this reaction, the enthalpy is X, right? Cool. Now, so basically what I'm trying to say, okay, actually guys, this is minus, and this is minus 53.7 because I know all neutralization reactions are exothermic in nature, isn't it? Heat will be released during a neutralization process, so obviously enthalpy should be negative. Hope you remember that. Enthalpy value negative means exothermic, enthalpy value positive means endothermic, right? Okay, fine. So now if I compare this value, like this 53 minus 53.7 with this X, okay, now what do you think is going to happen? So obviously as the strength of the acid decreases, right, the enthalpy value also decreases, in the sense that say this will be around, say I can tell minus 10 kilojoules per mole, right? So basically this value is going to become more and more positive, in the sense that it is going to approach more and more the positive value, more and more near zero, right? So obviously it cannot be endothermic, it cannot have a positive value, right? That means you have to have heat giving here so that the reaction happen. That all will not happen. So what I'm trying to tell you is that as the acidic strength of the acid decreases, the enthalpy value, the magnitude of enthalpy value decreases. That's what you need to understand. Okay, right? So we don't have to do problems on this. If you are interested, maybe after completing everything, we'll spend time on all this. But questions coming from these, like enthalpy preparation is very rare. Even if they ask you, maybe they'll just give two reactions and they'll give their enthalpy values like this and ask you to compare the acidic strengths, right? So obviously the one with magnitude, more magnitude of enthalpy is a stronger acid. That's what you need to understand. Is that okay, guys? Right? Fine. So that's about enthalpy of neutralization, right? Now the last enthalpy, which is there in our syllabus, right, is enthalpy of, okay, I think I'll write the short form only, right? So I have enthalpy of solution, delta H solution, right? So obviously now what you understand is you're going to make a solution, and obviously there are going to be some enthalpy changes happening in that, right? Okay, guys. Now I think we already spoke about it, right? How do you make a solution? I would have studied in your solutions chapter also. You need to make a solute. You need to have a solvent. All these things will be there. Okay. So actually, there is no direct definition for enthalpy of solution because it is a combination of two other enthalpies, guys, right? So enthalpy of solution is basically a combination or a sum of these two. That is my delta H hydration, or I would say in general solvation. If water is not the solvent, some other thing is the solvent. Delta H solvation or delta H hydration plus something called as lattice enthalpy. Okay, now that you have completed solid state, you must know what is a lattice. You must know what is the lattice enthalpy. Anyways, we'll see it again. No issues, right? So please remember this, guys. Enthalpy of solution is the sum of two other enthalpies, and the two other enthalpies are enthalpy of hydration or solvation plus the lattice enthalpy. Okay, now this particular thing has a logical reason behind this. Why do I sum up these two to get this, right? There is a thing, like, please understand, guys. Say first we'll talk about the lattice enthalpy, right? Fine. Now when you want to see, when you're going to make a solution, right, when the solution is not made, when the solute and solvent are in separate test tubes or separate beakers, what kind of interactions you'll have? Say I can say that I can have solute interactions, right, in the test tube, right, because only solute is there. Or say I can have solvent interactions, right? Say solute means, say for example, if I'm going to have NaCl, right? Say I'm going to have all these dipole interactions, dipole ion interactions, all the van der Waals forces, all these things that we are talking about. We're not talking about actual chemical bonds, no, right? So we're talking about the secondary types of bonds. That's what we say, the solute interactions. Solute interactions and solvent interactions are going to be there before you form the solution, right? Now what you have to do first, people, when you're going to mix these two, right? So what is going to happen? Obviously, you are going to break the solute interactions. You are going to break the solvent interactions. And one more thing you are going to make is solute solvent interaction, right? So this is how this happens after the solution is made, right? Now, whether it's going to be a good solution or not, whether the particular solute is going to be completely dissolved in the solvent, or like this is going to depend upon the energy, the amount of energy spent here, right? And obviously the amount of energy released here. Like here, see, obviously energy is released, here energy is absorbed, right? Because you're gonna make, break bonds here, you're gonna make bonds here, right? So obviously solute interaction, solvent interaction has to be broken, and solute solvent interaction has to be made, right? So as I told you, a particular solute, if it is going to be dissolved in a particular solvent, is going to depend upon these energy considerations, right? So if I want a good solution, guys, this E should be greater. That means the energy released should be greater than the energy absorbed, in the sense that the solute solvent interactions should be stronger than solute and solvent interaction. Only then, obviously, then what is the point, right? Already, if they have very strong bonds, why will they even break? And if they are not so, if they're not so strong, why will they even form? Right? So obviously the solute solvent interaction must be stronger than solute and solvent interactions, right? Okay, so you see that there are two energy terms coming here, and these two are the energy terms that are coming here also, right? So obviously when I have, for example, say if I dissolve NaCl and water, right? So we know what is going to happen there. I'm going to have hydration happening. We know what is hydration, right? Hydration is crowding of the water molecules surrounding the ions. Say Na plus ions, water molecules will surround. Cl minus ions, water molecules will surround, and that is what is called as hydration, right? So obviously, this we are talking about the solute solvent interaction. Whenever happens, the energy released is what is this? The solvation enthalpy or hydration enthalpy, right? And before that, obviously, you need to break the bonds between solute and solvent, and that is taken care by the lattice enthalpy. Okay, right? Fine. So this we understood. Now, there is, again, basically, if I want to define lattice enthalpy, define hydration enthalpy, we can do that. We will do that now. So please take down the definition for hydration enthalpy, people. Please take down the definition. I'm talking about hydration enthalpy. Okay. Right. So it is the enthalpy change occurring. It is the enthalpy change occurring when 1 mole of an anhydrous substance, when 1 mole of an anhydrous substance gets hydrated. Very simple, right? It is the enthalpy change occurring when 1 mole of an anhydrous substance gets hydrated. That's what is hydration enthalpy, right? Say now by looking at the statement, you can understand that there is an anhydrous substance and you're going to add water to that, right? And it is going to become hydrated. That's what is going to happen. Say, for example, if I tell you that enthalpy of hydration of, say, copper sulfate, okay, enthalpy of hydration of copper sulfate, if I say it's some X, right? How I'll write the reaction, we'll see. So we need to have 1 mole of anhydrous copper sulfate in the reactant side, right? And I'm going to add water to this. It depends how many water molecules I'm adding, because it is going to depend upon the structure. So when I add to this, so it is going to become CuSO4 dot 5H2O. For this reaction, the enthalpy change is mentioned here. That is delta X, delta H is equal to X. Okay, so I have 1 mole of an anhydrous substance getting hydrated. What is the enthalpy change in this reaction? Is what is called as enthalpy of hydration. Okay, guys, fine. So that's about hydration enthalpy. Right, now the questions will be very simple from this. They'll give you the hydration enthalpy, they'll give you the lattice enthalpy, and you have to find the enthalpy of solution. That's how it will be. Okay, now how will you go for lattice enthalpy? Right, so basically lattice enthalpy, how will I define it? Is, please go for it. Lattice enthalpy. We'll define lattice enthalpy now. So basically, we know what is a lattice, isn't it? Lattice is the structure, crystal structure. So we can talk about lattice enthalpy only for crystalline substances. We cannot talk about lattice enthalpy for any other things, because no other thing has proper structure, right? Lattice, crystal lattice is what you're talking about, crystal structure, right? So basically, you can understand what is going to be lattice enthalpy. It is the energy required to break the lattice, or it is the energy required to make the lattice. Like obviously the sign will be different, but the magnitude is going to be same. Again, I repeat. Lattice enthalpy is the enthalpy change occurring when like we don't even have to go for definition, guys. It's pretty simple. It's like lattice enthalpy means the energy required to break the lattice, or energy required to form the lattice. Either way, right? Obviously I'm going to have different signs, right? But the magnitude is going to be same. That is what it is called as lattice enthalpy, right? Now, how do you find lattice enthalpies, right? So there is no reaction as such, right, for lattice enthalpies. But there is a way by which you will be able to find the lattice enthalpy, right? There is, okay. Now we'll see how to find the lattice enthalpy. Right, let me make a page. Right. So we have something called as Born. Okay, one second. We have something called as Born-Haber cycle, right? So I think it should ring some bells because you should have heard it in your 11th class, which is not something new we are studying, right? So Born-Haber cycle is going to be helpful for me to find the lattice enthalpy of a particular crystalline substance. Okay, right. So what we are going to do here is just basically we are going to do the energy conservation, right? So we are going to just say that the amount of energy, the amount of energy spent should be equal to the amount of energy released, something like that. We are just going to have the energy conservation happening here, right? So you are going to put all the energy terms absorbed in one side, right? And you're going to make all the energy terms released on another side, right? And you can find the lattice enthalpy. That's what you're going to do, right? But this, as the name tells you, it's going to be a cycle. It involves a lot of other processes, right? Maybe if I give you an example that will make a lot of sense. Okay, fine. So guys, I have sodium, right? And I have chlorine, and say it is going to form NaCl crystal. Okay, NaCl solid. Easy, right? This is just a reaction, but please understand there are a lot of inside things which has to happen for me to end up with this. It is just not, obviously if you just mix sodium and chlorine, you'll just get NaCl. But that's what we see also in reality if you just make a reaction. But if you go to the inside, right, and see what exactly is happening, there are a lot of inside things are happening. We'll see what are those. Okay, now please understand, guys, sodium will actually be in solid state and chlorine will be in gaseous state, right? Okay, now please understand, this sodium has to form Na plus and this Cl2 has to form Cl minus, and this Na plus and Cl minus has to combine to form NaCl. That's how the reaction goes, right? Now the question is, now sodium is in solid state. First we'll talk about sodium, then we'll come back to chlorine. Okay, right. So please understand, sodium is in solid state here, right? Now answer my question. Can anything in solid state form any ions? You can just give me an yes or no. Can anything in solid state form ions? Okay, good. No, obviously not possible, right? So please understand, guys, if you want to form ions, that particular the particular metal should be in its aqueous state or in gaseous state. Only two things are possible. Okay, so if you want to form an ion, right, the substance should be either in aqueous state, that means it has to be dissolved in water, right, or it has to be in gaseous phase. Only two possibilities. Solids, pure liquids cannot form ions, as simple as that. Okay, so the first step in going for NaCl is that if at all I want to form sodium to form ion, obviously I require sodium in the gaseous state, right? Because sodium solid cannot form ions, I have to convert it into sodium vapors or sodium gas, right? So obviously there'll be an enthalpy supplied here. There'll be some energy supplied here, right? And you can see solid to gas is going to be sublimation, right? So I am going to call the enthalpy associated here as delta H sublimation. Very simple. Okay, sodium solid to sodium gas, enthalpy of sublimation. Right now, this sodium gas can now form ions. Na plus it can form. Now, easy, right? Now, sodium will form Na plus by losing an electron. Right now, tell me what is the enthalpy associated here? Quick, for this reaction.
Enthalpy of ionization.
Enthalpy of ionization, or it is a famous one. This ionization enthalpy, I. Right, the energy required to remove the electron from the valence shell. Normally, what we do, right? So this is my ionization enthalpy, right? So guys, if at all, maybe next thing I'll ask you to do. Okay, fine. I'll not break the surprise now. Fine. So I have ionization enthalpy to form Na plus an electron, right? And that's it. Sodium formed Na plus. Sodium's job is done, right? Now I have to go to chlorine, right? So I don't have space, so I'll write it here, guys. So chlorine is in gaseous state. No issue, so it can directly form the ions. But please understand, Cl2 molecule cannot form ions. Chlorine atom can form ions, right? So first what I have to do, I have to convert this chlorine molecule into chlorine atoms. Then only I can talk about making of the anion, right? So obviously I have to convert this into 2Cl minus, 2Cl atoms. But please understand, guys, I require only one chlorine. I don't require two chlorine. If I break this, if I supply the energy, it is going to become two chlorine atoms. Out of that, I require only one, right? Fine. So first, we'll come back to that later. Now tell me, what is the enthalpy associated here? Cl2 to 2Cl. What is the enthalpy?
Of atomization.
Exactly, right? So it's here going to be enthalpy of atomization, or I can call it as bond enthalpy, or however you want to call it, right? Now, we are telling that we always define all the energy value in terms of kilojoules per mole, right? Now, if I supply 1 full kilojoule per mole, I would say whatever the value, that much kilojoules per mole, if I supply for Cl2, I will end up with 2 chlorine atoms. But what I require is only half the mole of chlorine atoms, right? So I just go for half the bond enthalpy. Okay, it's not clear there. Please write it as half into bond enthalpy. Hope you understand why is it half into bond enthalpy, because like if I break it, I'll get two chlorine atoms, but actually only one is required, right? So if I substitute it, I'm just going to get 1 mole of chlorine atoms. That's it. Okay, so hope you understand why there is half bond enthalpy here, right? Now that's it done. So I formed the chlorine atom. Now I can go for Cl minus anion formation. So that is basically going to accept an electron to form Cl minus. And what is the enthalpy associated here, guys? What is the enthalpy associated here for this reaction? Something there.
Electron gain enthalpy.
Exactly, right? Even though we didn't see about all these enthalpies, I mean, in the sense we didn't see in the thermodynamics, but you have been studying this from your lower classes, isn't it? So obviously, whenever an electron is added to an atom, the energy associated here is what is called as your electron gain enthalpy, or it is all, like if at all you want to write a positive value, you can go for electron affinity. right? So electron gain enthalpy is the energy associated here, right? Now that's it. You have the required species with you. You have your Na plus, you have your Cl minus. Now they both will combine to form NaCl. Now this is where the crystal is getting formed, guys. Na plus and Cl minus will combine together to form NaCl. I told you, whenever you want to break a crystal or whenever you want to form a crystal, the energy changes required there is what is called as lattice enthalpy, right? So now what you're seeing, Na plus and Cl minus are coming together to make a bond, right? So obviously the energy will be released, and that energy released is nothing but your lattice enthalpy, right? So this is how the cycle goes, right? It's pretty simple. Sodium has to be converted to sodium solid. Sodium solid to sodium gas. Enthalpy of sublimation. Then you convert sodium gas to Na plus. Ionization enthalpy. Now that's about sodium. Now when I go for chlorine, first I have to convert chlorine gas into chlorine atom, in the sense chlorine molecule into chlorine atom. Now I want only one chlorine atom, so I supply only half the bond enthalpy. Then I go for this, that is making of Cl minus ion. There it is electron gain enthalpy. And at last you form sodium plus, you form chlorine minus. They will combine together to form NaCl. That's where the crystal is getting formed. So the energy released is what is my lattice enthalpy. Okay, right? Now now to the first point, what I said regarding Born-Haber cycle. You are going to put all the energies supplied in one side, right? And all the energy released on another side, right? So then we'll be able to find the lattice enthalpy. As simple as that, right? Energy absorbed is equal to energy released. This is what you need to understand from Born-Haber's. Energy absorbed is equal to energy released. This is what you need to understand. So keeping this in mind, if I just write the equation, it's pretty simple. Right, okay, before that. So you see, guys, enthalpy of sublimation is definitely energy absorbed, right? Ionization energy also you are going to supply. Bond enthalpy also you are going to supply. Yes, no issues, right? So obviously these three are the ones which are going to be energy absorbed values. Electron gain enthalpy is negative. You must have known it, right? Electron gain enthalpy is energy released, right? And again, lattice enthalpy is energy released, right? So if I just write the equation, I will be getting delta H sublimation plus ionization enthalpy plus half the bond enthalpy, very careful, or not full bond enthalpy, right? Half the bond enthalpy. Now these are the energies absorbed. Now these are going to be equal to the energy released, and that is my electron gain enthalpy, right? Plus your lattice enthalpy. That's it, right? And guys, all these values for a particular metal or particular element are already known. We have some information table, right, which will give not only this, all the other properties of an element, right? So all these four other things will be known: bond enthalpy, ionization enthalpy, sublimation enthalpy, electron gain enthalpy. All these things will be known, so you can find the lattice enthalpy. So this is how, through your Born-Haber cycle, right, you will be able to find out the value of lattice enthalpy. Is that okay? Right, now what is the time? I can spend one more example. I think it's worth it, right? Fine. Anyways, so now guys, you understood how NaCl works. Okay, right? Now I'll give you MgCl2, right? I want you to find the lattice enthalpy of MgCl2. I'll give you one or 2 minutes. Okay, so time is 7:37. 7:39 I'll give you, right? Go for the Born-Haber cycle and write this equation. Go for it. Draw the Born-Haber cycle for MgCl2 and get the equation for lattice enthalpy. Okay. Maybe one more minute. Okay, guys, I think you should have gotten by this time, right? So again, the reaction goes like this. I have Mg. I have Mg plus chlorine gives MgCl2. Now the reaction looks simple, but again, there are going to be inside things. Now again, Mg will be in solid state. It cannot form, what is that, ion. First, I have to convert Mg to Mg gas, and obviously here it is my enthalpy of sublimation, right? Now the thing is, obviously, you know what is the ion present? Ion present is Mg2 plus, right? So you cannot put directly ionization enthalpy and put Mg2 plus, because you know ionization enthalpy is specified for one electron at a time, right? One ionization enthalpy means only one electron I can take out. So it's not like one ionization enthalpy and you can take out two electrons. No, right? So how you have to write here is like this. I have the first ionization energy. One second, guys. Let me just bring it a little up. Okay. So I have the first IE. So I will be forming Mg plus. And after this, I go for the second IE. Then I go for Mg2 plus. Done. Mg is done. So now the only difference between last time and first time is you're using successive ionization enthalpies. First ionization enthalpy, form Mg plus. Second ionization enthalpy, form Mg2 plus. Pretty simple. Right. Now going to chlorine. Chlorine gas, Cl2 is there. Now please understand again the difference between last time and this time is that I require 2 chlorine. Right. So you have to supply the entire bond enthalpy, so that I will be getting 2 chlorine atoms, right? Now I have to form 2 moles of Cl minus, right? So again, remember, now obviously you're going to add electron to this and you're going to do it, but an electron gain enthalpy is defined for one atom, or I would say it is again defined for 1 mole of atoms, right? So since you have 2 moles of atoms here, you have to write 2 into electron gain enthalpy. Be very, very careful, right? So here it is full bond enthalpy. That's the difference last time. And last time I had only 1 chlorine. Here I have 2 chlorine to convert to 2 Cl minus. So I require 2 more, I would say 2 into electron gain enthalpy. And that's it. Now these two will combine together to form MgCl2, and the lattice enthalpy is released. Okay. So again, if you write the equation, it will be delta H sublimation plus first IE plus second IE plus bond enthalpy, full bond enthalpy, not half bond enthalpy. And these are the energy supplied, and energy released would be 2 into electron gain enthalpy plus the lattice enthalpy. Right? Done. That's it. Okay, so hope you understood. Like, how many of you got this equation, guys? Anybody got this equation, particular equation which I wrote here? This one? Anybody got it?
Sir, I just put it as 2 IE, sir, instead of IE1 plus IE2.
Okay, fine, no issues. Right, now that you got it, that's what is more important, right? So now I think any compound given to you, you'll be able to easily do it, right? Okay, guys, and that's about the second part of thermodynamics. First part talked about the first law, zeroth law. Second part talks about your enthalpies. And now you'll go to the third part. Third part talks about second law of thermodynamics, third law of thermodynamics, entropies, the Gibbs free energies, and all these things, right? That's a little smaller part. So that will start now. Any questions, people, till now in this chapter? Is there anything you want to know or any doubts you have?
Sir,
Right? Yeah.
sir, in this reaction, the final product we get is MgCl2 in the solid form.
Yes, solid form, yes.
Okay.
Because lattice is defined for, you can ask me, how is it possible? This will be in gaseous states, right? So yeah, that is defined like that only, Kana. Basically, when I write my lattice enthalpy equation, right? This is how I write. Basically, I write MgCl2 in solid form is going to form Mg2 plus Cl minus, 2Cl minus. This is how I write it also, right? So it is how lattice enthalpy is defined. You don't have to worry about how are you going to do it, right? Basically, you're asking like, sir, how will I convert the gas back to solid? Is that what you're asking, Kana?
Yes, sir.
Like I understand, right? So obviously, like it doesn't make sense, but still that is how it is defined. And if you ask me, are we really doing this kind of process in reality? The answer is no, right? These are just for calculation purposes. From some already known quantities, right? If I want to find the unknown quantity, like there are some assumptions which I have to do. This is not only here. Even if you go for higher levels of chemistry, when you go for labs and you go for little in-depth concepts, you have to assume certain things. There is no other go. But yeah, a nice question. How is it possible? Yeah, like not so like realistically possible. But yeah, that is how it is defined, lattice enthalpy. You don't have to worry. A solid crystal getting converted to ions. That is how it is defined itself. Is that okay?
Yes, sir. Okay.
Right? Okay. Fine. Is that your question? Did I answer your question, Kana, or is it something else that we ask?
Yes, sir. I was about to ask this question.
Okay. Cool. Right. Fine. So now we'll move on, guys. Any other questions? Anybody wants to ask? Okay, fine. I suppose there are no questions. Fine. Now we'll go to the next concept. Right. Fine. So we already know this, right? We are going to talk about a famous thing called entropy. It is denoted by the letter capital S. Okay, so we know what entropy is. Entropy is the measure of disorderness or measure of chaos. How much randomly a particular system is oriented. Excuse me. That is what is called as an entropy, right? Okay, so entropy is again going to be a state function. That means it is just going to depend on what is the initial state and what is the final state. How I reach from initial to final state doesn't matter. It's a state function, right? What else I have to tell you? Right, and we know how to compare entropies. Obviously, like I don't have to teach you like 11th class kids that so the gases will have more entropy than liquids. Liquids will have more entropy than gases. So we don't have to go into those details. You don't have to worry about it. But what I'm interested in, I'm teaching you is about the mathematics of entropy. Right? Fine. Now, how am I going to mathematically define entropy is what you're going to see, and we're going to see. Right? Again, guys, measuring absolute entropy is not possible in the sense that measuring the S value at a particular time for a system is impossible. Right? What I can measure is change in enthalpy, change in entropy, delta S. That I'll be able to find. That I can see that that is common thing for all the thermodynamic quantities you have been seeing, right? Say be it H or be it internal energy or whatever it is, you will not be able to find the absolute value. All you can find is there a change in the enthalpy, or is there a change in internal energy? Is there a change in entropy? Those things only we will be able to find, right? Okay, so this delta S, right? This is how I mathematically define it. It's equal to Q reversible divided by temperature. Very, very simple. Okay, right? So this is how I mathematically define my change in entropy. Q reversible divided by temperature. Okay, now I can give you a logical explanation of why this equation is like this. Okay, so now we'll talk about why this reversible is there, but we can just understand that obviously there is going to be more increase in enthalpy. Sorry, I'm stuck at enthalpy, guys. I'm really sorry. Right, so there is going to be more increase in entropy. That is, the delta S is going to keep on increasing. Obviously, if I supply more and more amount of heat. Is it not? Right? Say I have a liquid, right? If I supply an amount of heat, it is going to become a gas. So obviously you see that the entropy is going to increase. Right. Okay. So this makes sense. Why heat is in there in the numerator makes sense. Right. Now, why is it that the temperature is the denominator? That actually is little surprising, isn't it? We generally say that when I have higher temperature, I have higher entropy. Right. But please understand, we are talking about change in entropy here. We're talking about delta S. Right. So obviously when when I say when I say that we are talking about change in entropy, so obviously when I have lesser temperature, right? When I have lesser temperature, increase in entropy is easier. Is it not? Right? But say I already have 100 degrees Celsius. I already have a high amount of absolute enthalpy. Again, absolute entropy. Right? So obviously increase in entropy in that particular case is different. I mean, different in the sense difficult. Again, I repeat, right? Say I have two bodies at 100 degrees, 0 degrees Celsius and 100 degrees Celsius. Right? Now this will have very less value of absolute entropy. This will have very high value of absolute entropy. But now you're talking about change in entropy. Right? Now this already has increase in entropy. Say for example, if I give if I go from 0 degrees Celsius to 5 degrees Celsius, and if I go from 100 degrees Celsius to 105 degrees Celsius, right? So please understand, even though the change in temperature is only 5 degrees, right? Now here the delta S is going to be greater than the delta S from this case, because this already has some higher entropy. Changing 5 degrees is not going to change much in the entropy value, but this has already lesser entropy. But giving some, like increasing the temperature, obviously you see that the entropy is increasing more in the delta S value is more than in this case. Right? So that is the reason why we keep temperature in the denominator. Lesser the temperature, higher the increase in entropy. That's what you need to understand. Okay, right. Now, why this reversible? Okay, why do I go for this reversible thing? Right. Now, please understand, guys, if you can see from this, we know Q is the path function. Isn't it? Q depends on the path. Q and W both are going to depend on the path taken. It is not only going to depend on the initial and final state. It is also going to depend upon what is that? Your path taken also. Right. Now, again, going with path function, as I told you, is a little difficult, isn't it? Like if I just know the initial and final state, if I can work it out, it's pretty easy for me. So I really don't want to go for path function. Right. So what I do is that since I want my entropy to be a state function, right? So I would say, I don't know, some of you knows Hindi, even I don't know, but I know this word is called jugaad, right? So some KD thing I do, right? So that I'll be able to make this entropy, change in entropy, a state function. Now what I do, now if I make sure that any process is assumed to be only happen in one path, there is only one path. Obviously, then there is no question of having different path. There is no question of path functions itself, right? Because any process, if it is assumed to be assumed to go through only one path, there is no question of path function. Everything is a state function, right? So if I can make sure that every process happens through only one path, my job is set, and that constant path is what is this reversible path. Okay, irreversible can have 1,000 ways to go. Reversible has only one way, the slowest possible way, whatever it is, and that is what is reversible. So what I'm trying to do is that I am trying to make delta S a state function, but even though Q being a path function, I convert Q to Q reversible, which becomes a state function. That's what you need to understand. Because now making sure that the path is reversible only, right? I make sure that there is no question of path functions. This is going to be a state function only. Is it okay? Right? Fine. So now delta S is equal to Q reversible by T. Fine. Now we understood what is the importance of Q, reversible, and T being in the numerator, being in the denominator, all those things we saw, right? Okay, now your second law of thermodynamics, right? Your second law of thermodynamics is going to depend on the change in entropy, right? And please understand, guys, just like how you have for all the quantities, when you want to find the thermodynamic property of the universe, you have to sum up your system's value and the surroundings' value. Same goes with the entropy also, right? So I would say delta S universe will be equal to delta S. If I write S by M, is system, guys, right? Okay, let me push this to the side. Right, so delta S system plus right, where were you? 1 second, guys. Yeah, so delta S system plus delta S surroundings. Right, now why I tell you is because your second law is going to be based on this. That's why I tell you this now, right? So guys, now comes the famous second law of thermodynamics, my favorite law, like compared to zeroth law, first law, and second law, third law. My favorite one is second law, right? So we are going to see second law of thermodynamics. Okay, and guys, there are so many different scientists who gave different statements for second law, right? So even though you see that they're going to talk about different things, the definitions are different and all that, eventually everything means the same. You will be able to appreciate maybe when you go for some higher levels of chemistry, right? So for now, we'll just look at the statements and we'll just validate them, like in the sense that we'll just try to prove them that that is correct, that the law is correct. We'll take some real life examples and try to prove it. Okay, fine. So the first way of defining your second law is with the help of this entropy of the universe. Okay, now please check down, guys, the definition. Right, now please understand, we are going to speak about spontaneity. So basically, second law, the first application is that it is going to give me the direction of a spontaneous process. Right? The second law is going to help me find out the direction of a spontaneous process. Right? We know what's a spontaneous process. Spontaneous process is something which we don't have to do anything. It is going to happen on its own. Say, for example, water going from higher level to lower level, right? Heat moving from lower body to colder body, right? Say at 100 degrees Celsius, water getting boiled, you are not doing anything. If you just apply the temperature, right? You don't have to, even if you do this thing, right? It is going to keep on boiling. Say melting of ice at 0 degrees Celsius, at if I have 0 degrees Celsius, obviously the ice is going to melt, right? So all these are spontaneous processes. You are really not doing anything, right? So if I want to talk in terms of chemical reaction, if I just put sodium in water, what will happen? I'm going to have a violent process, violent reaction happening, right? So again, that is a spontaneous process. So anything like, so please, like with the help of second law, we are going to give direction, which side, right? The reaction or say the process is going to happen. Like, that's what we're going to define. Please take down the definition, right? So the direction of a spontaneous process should be the direction of a spontaneous process should be in such a way that the entropy of the universe such that the entropy of the universe increases, right? Such that the entropy of the universe increases, right? So I'll repeat the statement, guys. So the direction of a spontaneous process should be in such a way that the entropy of the universe is increasing. As simple as that, right? So please look at there. It is not entropy of the system. It is entropy of the universe. Please be very careful. A lot of students do a mistake here, right? Say, for example, guys, let me ask you this, right? Say, if I go for freezing, right? If I go for freezing, right, and basically freezing point of water is 100 degrees Celsius. Sorry, 0 degrees Celsius, right? So what is happening there? Water, which is in liquid form, is getting converted to solid form, freezing, right? So again, when I compare the system's entropy change, that is, when a liquid becomes a solid, obviously the entropy is decreasing, isn't it? But again, that is a spontaneous process. Why? Because you are looking at only the system's value. In system, yes, there is a decrease in entropy. I am not denying it. But it's not only about system for a spontaneous process. You have to take the system's value. You have to sum it up with the surroundings value. Then check the value for entropy of universe. And if that value, entropy of universe, one second, guys, right? So if entropy of universe is greater than 0, that is what is the thing which you have to look for. If you find that for that particular process, entropy of the universe is greater than 0, then it's a spontaneous process. If it's less than 0, then it's a non-spontaneous process. So please be very careful. Okay, you are not only going to talk about system, you have to speak about surroundings also. Sum it up, and that value, if it is greater than 0, then it's a spontaneous process. Okay, now let me give you a real life example, right? So to prove you that this is actually the thing. Okay, so for that purpose, let me take melting of ice. Okay, so let me take melting of ice and we'll see what happens there. Right. Okay, cool. So we'll try to do it. Maybe I wish I should take a small bigger next page. Okay, I can try. I can continue here only. Let me maybe little. Okay, fine. Right. So we are talking about melting of ice. Right. I'm going to prove it to you that melting of ice, obviously we know it's a spontaneous process. That's what we see in reality. But I'm going to prove to you that this is also going to happen. Delta S universe is going to be greater than 0. Right. Okay. Fine, guys. So melting of ice happens. So first, let me calculate delta S. Right. I'm going to calculate delta S of the system. Right. So here, when I say system is this. When I have melting means solid to liquid. This system is what I'm talking about. So solid to liquid water. That equilibrium is what I'm talking about. Okay. So when I talk and I do this, now please understand. Okay. So I know delta S is equal to Q by T. If you can remember here, where are you? Right. So you can see from this equation, this is the equation I'm going to use, right? Delta S is equal to Q by T. Okay. Right. So now that equation only I'll use. Now, what is the Q value which I have to substitute? Obviously, the temperature here is going to be 0 degrees Celsius. No doubt about it. Right. So divided by the temperature which you're talking about is 0 degrees Celsius, or I can write it as 273 Kelvin. Right. That is okay. Oh God. This touch sometimes, I think there's a problem with the stylus, not with the touch. Right. Okay. Right. So I have 273 Kelvin in the denominator. That is okay. 0 degrees Celsius. Now, what should come in the numerator? You think and tell me. Any guesses? We're talking about heat, right? And we are talking about the heat which is supplied at 273 Kelvin, not the entire heat you have been supplying, right? So at 273 degrees Celsius, you are going to start melting the ice, right? So obviously you are going to supply, it's not like I am going to supply, but there is some heat which is getting supplied to the ice, which is keeping on, which is making sure that the ice melts and converting completely into the liquid water. Right. What is that thing which I have to substitute here? Tell me. In the numerator. Let me see if someone can answer this. Maybe in the chat box something is there. Okay. I am all eyes and ears. I'm looking at you. I'm looking at your text. And I'm hearing you. Any guesses? What is the heat which I have to, or what is that energy term which you're talking about there in the numerator? No answers. Okay, right? So guys, we're talking about a fusion process, melting process. It's pretty simple that I have to use delta H fusion. That's it, right? Right, delta H fusion is what I have to use. Enthalpy of fusion. If it was boiling process, I would have used enthalpy of vaporization. Right? So it's pretty simple. That is the heat which you're supplying. Correct? So delta H fusion divided by 273 Kelvin is what is the system's value. Now, please understand it is now the sign also is very, very important. Okay. Now, please understand that it is the heat is going to get supplied, obviously, right? So this is a positive value, right? This is a positive value. Right now, that is about the system. Guys, any doubts here? Why is it enthalpy of fusion? Because we're talking about solid to liquid melting process, that's fusion, and the temperature at which it is happening is 0 degrees Celsius, that is 273 Kelvin. Very simple, right? And that's about the system. Now, when I go to the surroundings, oh God, what is wrong? Right? When I go for surroundings, now tell me, what is the temperature I have to supply? What is the temperature value which I have to put to the denominator? Tell me.
Room temperature.
Absolutely true, right? So this is happening at 0 degrees. It is now the surrounding is not at 0 degree. That surrounding is our surroundings, which is the room temperature. So I can just put it as 25 degrees Celsius approximately we'll keep. So let me put it as 298 Kelvin, assuming it's 25 degrees Celsius, right? And what is the numerator? Now, please understand, guys, this enthalpy of fusion, which we have put here, right, is actually coming from the surroundings. That means the system has acquired the heat. That is why it is positive. And where is this heat coming from? This heat is coming from the surroundings only. We are not doing anything. It is coming from the surroundings, right? The surroundings would have lost heat, and the same amount of heat which would have been absorbed here is the amount of heat which have been lost, right? So now here also it is going to be enthalpy of fusion, but except that I am going to put a negative sign. Please remember the sign conventions. Heat absorbed is positive. Heat lost is negative. Surrounding loses heat, loses this much amount of heat to the system, right? So system will have a positive value of that, right? And the surroundings will have a negative value of that. Done, right? Now it's pretty easy, guys. Now I can go for your delta S universe, right? Now that will be equal to this value, enthalpy, basically, right? If you calculate it, enthalpy fusion, I can just take enthalpy of fusion outside, right? Now it is going to be 1 by 273 minus 1 by 298. And obviously you will see that this value is going to be greater than 0, indicating that it is going to be a spontaneous process, right? So yeah, not only this case, I can take any case, any spontaneous process, and I can prove it to you like this. Okay, take the system's value, take the surroundings value, but be very careful with the science people and put the temperatures accordingly. And I will be able to, or not only me, any you also will be able to prove it to yourself that delta S universe, if I have greater than 0, that is going to be a spontaneous process. Okay, right? So that is one form of looking at first law. Sorry, second law, right? For any spontaneous process, delta S universe is going to be greater than 0, right? Okay, now we'll go for the next statement, right? This is talking in terms of spontaneity, right? Now there are other ways of looking at it, right? Now, second way of second law, please take down the statement. There cannot be any engine. There cannot be any engine which can convert heat into 100% work, right? This thing is, the statement is, there cannot be any engine which converts heat into 100% work. Okay, that's a very simple statement, right? Now, we will try to analyze it, right? Okay, so we'll just take an example of our vehicles which we ride in our way, scooters or bikes or whatever it is, right? So we know what happens there, right? So basically there's a fuel tank, you add the fuel, so the fuel goes to the engine. So what happens there? The fuel is burnt, is it not? And there is a lot of heat energy produced, and this is the heat which you're talking about, right? So you supply heat. Where is the heat coming from? By the burning of fuels, right? So this heat is actually going to get converted to the work in a sense, the mechanical work. The vehicle is moving, or the inside, I don't know whether you have seen an engine. You will have pistons inside. You'll have, say, 4-stroke engine, means up, down, the 4 strokes, right? The piston goes up, down. I think that is 1 stroke. Second stroke will be again up, down. Third, so if I have a 2-stroke engine, means I'm going to have 1 up, down, second up, down, right? If I have 4-stroke engine, the piston moves up and down 4 times. That's what you need to understand. So anyways, so there is going to be some amount of work done, because whenever piston goes down or goes up, I know expansion or compression work is going to be done there, right? So what is the source of energy for this work being done? The source of energy for this work being done is coming from the heat, which was produced due to burning of the fuels. Okay, so again, I repeat, the overall process is like this. I have some fuel that is getting burnt, a lot of heat energy is produced, and that heat energy is converted to mechanical energy, or say some form of work in the engine. Say the turbine rotates, or the piston goes up and down, or the vehicle moves. Either way, whatever it is, you will be able to speak it that way. Okay, right? So what is the statement telling you is that if there is some amount of heat produced, right? If I give some amount of heat to the engine, right? There cannot be any engine in the world, even if, like, I don't know how much of a amount of energy, I mean, how much amount of money I spend, even if I go for a Rolls Royce or whatever it is, right? There cannot be 100% conversion of heat into work, in the sense that, say, if you have 10 joules of heat with you, right? You cannot have 10 joules of work extracted. Impossible, right? That's what the law says, right? Say I can have, say, maybe like 6 joules, 7 joules. Like generally, the normal motorcycles which we have, right, will have an efficiency of, say, 50%, 60%. Right? So if I have 10 joules, only 5 or 6 joules is actually used for running the vehicle. Right? Now, what happens to the last other amount of heat? Any idea? What happens to the remaining heat which was there? You should follow law of conservation of energy, right? Like it just cannot disappear, something like that, right? So what do you think is happening to that rest of the amount of heat? What is happening? Any idea? I have 10 joules of, yeah.
It goes out into the surroundings in the form of other forms of energy.
Yeah, it goes out into the surroundings in the form, not in the form of other form of energy, just heat only, right? So why do you think when you ride your vehicle for a longer period of time, your vehicle becomes hot? Isn't it? Why is that happening? Because of this only, right? Because there is some amount of heat energy produced. Some of it are converted to work, and the rest of it are going into the surrounding as heat loss, right? And this heat loss is an unavoidable consequence. Whatever you do, right, you will always find some heat loss. Not only in that, people say, if a fan runs for a longer time, you will see that the fan would have gotten hot. If a tube light is on for a longer time, if you touch it, you will feel that it's hot. Or even the simplest of process, if I just clap my hands, I hope you have heard it. Like if at all you had have clapped enough, you will find that your hands have become hot, right? So what I'm trying to tell you is that whatever be the work, whether we do it or someone does it or some appliances does it or an engine does it, whoever does work, right? Along with work, there will always be some heat loss. Okay, because obviously you are obviously for doing work, we have to get the heat energy, and we are the same, right? Obviously the food we eat is getting digested, the heat is produced, and that is the energy source for us, right? So again, we are also engines only, we are also taking up heat energy, we are converting into work, and obviously you know that our body is going to become hot, no matter whatever you do, right? So I hope you understand this second law is actually a very this form of second law, which I like it very much, rather before the rather than the first statement in which talks about entropy. This is a very fascinating statement for me, right? So whatever you do, these are small things which we don't see, which we don't appreciate, which while we see it in nature, but science, yeah, when you learn it, you will actually try to appreciate even the smallest of thing nature gives you, right? So anyways, so what I was telling is this heat is an unavoidable consequence, right? Sir, you can ask me, sir, is there any way that I will be able to violate the second law? That means if I have 10 joules of heat, can I convert it into 10 joules of work? Is there any way which I can do? The answer is yes. There are two ways, right? Oh, I am contradicting my own statement. Wait for it, right? So I said that there can be two ways by which you will be able to do this, right? First thing is that when you can do the process at 0 Kelvin, right? So if you can do the process at minus 273 degrees Celsius, 0 Kelvin, right? So then it is possible. Okay, right, fine. What is the next way? Next way is if you do the process 100% reversibly. We know what do you mean by 100% reversibly, right? Infinitely slow, right? Okay, now two things I told you, and obviously both these things are not achievable in nature, in the sense that 0 Kelvin cannot be reached. Till now, we have so much sophisticated instruments, but we are not able to reach 0 Kelvin. We can reach, say, minus 272 point something, but not exactly minus 273. That's what we are actually seeing now. Okay, right? So 0 Kelvin cannot be reached, right? And obviously, you cannot have 100% reversible process, right? That means what? The process should not even come to an end. It's an infinitely slow process, right? Say, like, 1 second, like maybe if I can. Right? So maybe if I show you my video. Oh, okay. It's flipped. No, guys, it's not good to show. Fine, no issues, right? So maybe if I try to clap as slowly as possible, actually I'm clapping, right? Maybe you will not even realize it. But if I do it very slowly, right? Obviously you see that the amount of energy, the amount of heat loss is going to be pretty less, right? Now this again you can understand from the vehicle point of view, also a motor vehicle point of view. Say if you're going to drive the vehicle very fast, right, the efficiency is less, right? The mileage will be less. But if you're going to drive it at a little slow pace, right, obviously the amount of heat loss is less, and the vehicle also gives you good mileage, right? So the slower the process you do, right, more and more is the efficiency. That's what you need to understand. Okay, right? Fine. So that is about your second law of thermodynamics. Okay, right? We'll speak more about this entropy, right? So this entropy, I want to speak. There are certain things which you have to know. I'm going to give you formulas, guys, for different types of processes, right? Say if volume changes, if what to say, your temperature changes, all these things, how my entropy is going to change. I'm going to give you an equation. Okay. So this equation is very important. This is definitely like there are so much chances that the problems might come from this. Please take down the equation. Delta S is equal to NCV ln T2 by T1. There are derivations for this, guys, but we really don't have to go through this, right? So NCV ln T2 by T1 plus N, I think it is, okay, NR ln V2 by V1. This equation you have to remember, or like, see, if at all you don't want to use ln, right? You can use log and multiply the whole thing by 2.303. Okay, right? If at all you want to use log to the base 10, right? So CV value, you know, number of moles, final temperature, initial temperature, R value, depending on what is the unit. Okay, I forgot to tell you about the unit of delta S. It is going to be joule per Kelvin. Is it not? Heat by temperature, or you can even write calories per Kelvin. Anything is fine for me, right? So again, R value will be accordingly used. If you want the R value, if you want the answer in terms of joule per Kelvin, use 8.314. If you want the answer in terms of calories, use R value as 2. Okay, so this is the value. Now say if it is going to be an isothermal process. Okay, if it is going to be an isothermal process, what will happen to this equation? So obviously T2 and T1 are same. So this equation is not there. It is going to become 0. Only this term will be there. Right. Same way, say if I have an isochoric process, that means if I have a constant volume process, right? So at that time, this term will become 0. Only this term will be there. Right. And say now I can even have one more equation. I forgot to tell you, instead of V2 by V1, I can even put P1 by P2. Right. So I have delta S is equal to, or this, again, you can write the statement equation again. Instead of this, I can even write NR ln P1 by P2. Okay. So this also works. And NCV ln T2 by T1 plus either in terms of volume or in terms of pressure, like depending on which is given in the question, you will be able to use it accordingly. Okay, so this is a very simple statement, guys. They will just tell you there is helium gas, 1 mole of helium gas undergoes a change in temperature from 100 degrees Celsius to 105 degrees Celsius. Find the change in entropy. Pretty simple. They have not given anything about the volume, so you don't have to worry about it. They have given that the temperature is changing. You know the CV value of hydrogen gas, number of moles is given, so you can calculate what is the enthalpy, entropy value. Okay, right? Fine. So this I want to tell you, and one more thing is there, another equation, right? So that is for entropy of mixing. Right. So what do you mean by mixing is, say when I mix two gases, right? Say I have N2 gas, H2 gas, I just mix them, right? So obviously there will be a change in entropy there also. Okay. So again, I'm directly going to give you the formula again. This has a derivation, but we don't have to spend time on that. So entropy of mixing is, R into Xi into ln of Xi. Okay. So it's basically R into Xi into ln of Xi. Okay, let me tell you what is this, right? So this Xi is mole fraction. Right, this Xi is mole fraction. So they basically, if I tell you, if I just do it like this, I have say 2 moles of N2. Okay, 2 moles. Okay, maybe I'll just bring it a little up. Right. So if I say that I have 2, okay, sorry. Right. So if I have 2 moles N2 and say 3 moles of H2, if I have, I told you that I have mixed it, right? And I ask you, what is the enthalpy change of this mixing? It's pretty simple. First thing, what will you find out is the mole fraction of both of these, right? So X of a okay, X of N2, if I have to calculate, we know how to calculate, right? So number of moles is the component divided total number of moles. So it will be 2 divided by 5, 2 moles, total moles is 3. Same way for X of H2, it will become 3 divided by 5, right? That's it. Now go to the equation. How will I do it? Now enthalpy of mixing, delta S mix, maybe I'll write it a little more, mix space I'll make. Right, so entropy actually of mixing these two gases will be R value. Again, you want however the answer you wanted, R into Xi into ln of Xi. Sigma is summation, right? So Xi is 2/5 into log of 2/5. And guys, since I'm using log, log I have to multiply by through 2.3. Don't forget. So 2/5 plus log of 2/5 plus 3/5 into log of 3/5. The whole thing into 2.303 is what is the answer to this question. Okay, so hope you understand what you mean by entropy of mixing of two gases, right? It is sigma xi into log of xi. I mean, you have to multiply by 2.303, and R you have to use accordingly to the units asked. Generally, it will be 8.314 only, because generally we go for only joule per Kelvin. Okay, so only three formulas for entropy, guys. One is Q by T. The other one is this one, right? I mean, I didn't mark it. Okay, this one. Right, and the last one is for entropy of mixing, this one. That's it, only three formulas you have to remember. Okay, and what is the time? 8:25. Okay, guys, can I just take 10 more minutes? I'll complete the chapter by myself. It's pretty simple, right? Okay, I'll just take 10 more minutes. I'll not take much of your time, don't worry. Okay, right. Now that's about entropy. That's about second law. That's about the things which you have to know. Now the last thermodynamic quantity which I have to introduce to you, which has been already introduced to you and you have been using it a lot of time, is my delta G. Right. Okay. Now, why is it happening like this? Okay. Delta G I know is change in Gibbs free energy. Correct. Right. So now how will I be able to define change in Gibbs free energy? I would say it is the useful work which can be extracted from a reversible process. Again, I'll tell you, it is the useful work which can be extracted from a reversible process. So basically this is nothing but W reversible in most of the cases. Okay. This is equal to W reversible in most of the cases. Okay, so anyways, you don't have to worry about the definition as such, right? Now, why are we even going for delta G, right? So we already know what is the thing. We define spontaneous process in terms of delta G. We say that delta G should be less than 0 for a spontaneous process. All these things we know, right? Now see, we already have a criteria for spontaneity, right? That is delta S universe should be greater than 0. That's what we have. Now, why are we going for delta G? What is that advantage we have, right? Now, the advantage is, people, in case of your entropy, right, you have to calculate the change in entropy for system. You have to calculate the entropy change for surroundings, and then you have to sum it up and then check whether that value is greater than 0 or less than 0. And accordingly, you have to decide whether the process is spontaneous or not. But the advantage with delta G is that you are going to do it only for the system. Right? You are going to do it only for the system. Right? That's the major advantage. Okay, right? Okay, so now this is the one thing. So the first thing is, it is going to be nothing but the W reversible, and I know for delta G should be less than 0 for a spontaneous process. And the advantage over using entropy is that I'm going to use it on, calculate only for the system. Okay, now there are various other equations, you know, right? So I have delta G is equal to delta H minus T delta S. So according to the values of your enthalpy and entropy, the process can be spontaneous at higher temperature or lower temperature. All these things, temperature also plays a role. Other equations is delta G is equal to delta G naught plus RT ln QC, right? So when I say not represents the standard value, right? Standard value in the sense I have 1 atmospheric pressure and 25 degrees Celsius room temperature and 1 atmospheric pressure. That is what is delta G naught. Now this QC, you know what is QC? QC is reaction quotient. We'll speak about it more when I go for equilibrium, right? It's simple only, right? Now I have this separate equation for delta G naught itself. Delta G naught is going to convert it to the equilibrium constant. So that is equal to minus 2.303 RT log of Kc. This is another equation. And you know, in even your electrochemistry, I have an equation. Delta G naught is equal to minus NF E naught of the cell, right? So again, this is another equation for delta G. I think that's it. These should be enough, right? So you have to know this equation, this, and obviously this. 4 equations for delta G. Okay, and problems are going to be pretty easy, right? Delta G. Now, see, how we did problems on enthalpy, like say there are 2 reactions given to you and the enthalpy values are given to you. So when you add 2 reactions, you add the enthalpy value also. Same things can be done for your delta G also, because that is also an energy term. Correct? So whatever the operations which you saw was possible for delta H, all the operations are possible for delta G also. The problems can come maybe from that also. Easy. Right? So other than that, you just have to know the equations, which you already know. We have completed the chapter, guys. Done. Any questions, guys? Any questions from all these we learned? Okay, so next chapter I would love to take would be an organic chapter, because we completed 1 physical, 1 organic, 1 inorganic. We'll go for another organic. So that would be hydrocarbons. Okay, and guys, regarding like, see, you can expect me teaching like this in depth to you only for 11th. What is that? 11th concepts, right? For 12th concepts, I will not be teaching the entire chapter like this, right? I will be teaching you then and there where is required, but we'll be concentrating majority on problem solving, because you already know the theories, right? There and there some things might not be there in NCERT. That alone I'll tell you, right? And we'll go for problem solving majority for all your chapters, right? Obviously organic, I'm thinking what we can do, but for your physical chapters, electrochemistry, chemical kinetics, solid state, and all that, we will actually go for only problem solving, like, because there is nothing much. 99% everything is covered in NCERT itself regarding physical chemistry, at least your other 3 chapters: electrochemistry, chemical kinetics, and what is the solid state. Okay, organic, yes, I have to go a little depth, right? So we'll see what can be done. So yeah, and that's it, guys. That's it for today. The class is done. Any questions? Okay, so I hope there are no questions. Fine, guys, we'll meet again tomorrow, right? So tomorrow I'll be starting with hydrocarbons. Is that cool? Not hydrocarbons. Like, I'm thinking like there is a specific way of taking organic, but I don't know. Okay, we'll see. We'll see. I'll just plan up something. Right? Okay, fine, guys. Thank you so much. We'll meet again tomorrow.
Thank you, sir.
Thank you, sir.
Thank you, sir.